Hello friends, in this video we are going to see how is the stagnation point and how to calculate pressure at stagnation point. So let's move on to the video. When rigid body is surrounded by a fluid, then in that case there exists a certain point on a body at which velocity of flow, that is local velocity of flow, is remains zero. So if this is the direction of flow of fluid and there exists a rigid body like this, then the flow in frontal face will get diverted, will move something like this as shown in figure. So we will have a point where local flow velocity will be equal to 0. So that point is called as stagnation point. There are total 3 parameters. First is velocity, second is pressure, and third is temperature. If velocity at stagnation point becomes 0, it results into increase in pressure as well as increase in temperature. So study of stagnation point plays very important role in analysis of the structures which are prone to high fluid velocities. Say for example aeroplane or any racing car, etc. So at the tip we have to provide a particular type of material which can sustain at high temperature and pressures. So this is the reason, because at stagnation point there is increase in pressure as well as increase in the temperature. So now let's move to actual derivation for stagnation pressure. Let us assume that there is a flow of fluid as shown in figure surrounded by a body, a rigid body. This is a rigid body. So there is a diversion of this line at point 2, and this point 2 is nothing but the stagnation point. As usual, when we want to calculate pressure at a particular section or particular point, then in that case we apply various available equations which are known to us. One of equation is Bernoulli's equation, that is energy equation. So we will try with Bernoulli equation. Let us consider some assumptions. First assumption is that fluid is compressible, means I am talking about air and not liquid. Secondly, surface is frictionless. This surface is very smooth is our assumption, so that we are neglecting various losses occurred due to friction. Third assumption is conditions are adiabatic, means no entry of heat or no exit of heat from the system. So these three are the assumptions. Let us consider, according to Bernoulli equation, P1 upon rho 1, this multiplied by K upon K minus 1, plus V1 square upon 2G plus Z1 equal to k upon k minus 1 p2 upon rho 2 plus v2 square upon 2g plus z2. Rearranging the term, we can have a common term k divided by k minus 1. So k divided by k minus 1 p1 upon rho 1 minus p2 upon rho 2 on one or the side, and on another side we will have v2 square minus v1 square upon 2. These z1 and z2 are get cancelled because we are considering z1 equal to z2 from the known datum line. So we have equation in simplified form like this. As we have considered condition as adiabatic, it means that p1 upon rho 1 raised to k is equal to p2 upon rho 2 raised to k, or p1 upon p2 is equal to rho 1 raised to k upon rho 2 raised to k, or rho 1 upon rho 2 equal to p1 upon p2 bracket raised to minus 1 upon k. So this is for adiabatic condition. So equation becomes k upon k minus 1 into p1 upon rho 1 1 minus p2 upon p1 minus rho 1 upon rho 2 equal to v2 square minus v1 square whole divided by 2. We have just replaced this term, these terms, by considering the ratio by taking p1 upon rho 1 as a common factor. So we will have one of the term to be get introduced, and that is c. We will call it as c1, that is equal to pressure wave velocity. To introduce c, we have to know the relation, and that relation is c1 square is equal to k into p1 upon rho 1. So this is the relation. p1 upon rho 1 is already seen in our equation over here. So we will replace it by remaining term. So we will have v2 square minus v1 square upon 2 is equal to, this gives us p1 upon rho 1 is equal to c1 square upon k. So we will have our equation as this is equal to c1 square divided by k minus 1, that k will get cancelled in bracket, remaining term will be as it is. We will modify it by considering the raised to power k. So we will have equation as 1 minus P1 upon P2 to the power 1 minus K upon K. This step is directly taken from this step because in previous derivation we have already obtained this result. So 1 minus P1 upon P2 raised to power 1 minus K whole divided by K. I want the calculation related with ratio P1 upon P2. So first of all, I will take this term on opposite side. I will have value as V2 square minus V1 square divided by 2 into K minus 1 upon C1 square is equal to 1 minus P1 upon P2 to the power 1 minus K upon K. I will have ratio P2 upon P1 as 1 minus K minus 1 upon C1 square in bracket V2 square minus V1 square divided by 2 K upon K minus 1. In this relation, we have multiplying factor of K minus 1 upon C1 square to the whole bracket. If we want to simplify, then in that case we will have ratio V2 square upon C1 square as well as V1 square upon C1 square. So that ratio is nothing but the Mach number square, M square. So we will consider a value of Mach number that may be more than 1, that may be equal to 1, that may be less than 1. As velocity is reduced, is close to 0, it means that Mach number is less than 1. So this is valid case. So when Mach number is less than 1, we have this ratio K minus 1 upon C1 square into 2. I am highlighting the portion. Just look at the portion, highlighted portion. So now I am talking about this ratio. So then 1 upon 2 K minus 1 M1 square. If this value is less than 1, so something square is again become less than 1, and that multiplied with K minus 1 and at the denominator will give us the less value. So then this is also less than unity. This right hand side can be expanded by using convergence series. So by using convergent series, expansion is this P2 upon P1, P1 upon P2 upon P1 equal to 1 plus K by 2 M1 square plus K by 8 M1 raised to 4 plus K 2 minus K divided by 48 m1 raised to 6 plus so on. There are so many terms. Here we will separately calculate the value of, I want to calculate the value of P2. It means that this P1 should get multiplied to another side. So P2 is nothing but the stagnation pressure. So now onwards I will use the word PS, stagnation pressure PS is equal to, I am directly multiplying this P1 with other side. So I will have P1 plus P1K m1 square upon 2 plus P1K m1 raised to 4 upon 8 plus P1K 2 minus K m1 raised to 6 whole divided by 48. So I have various terms P1 plus something addition. So I will calculate the value of this term. This term is P1K m1 square upon 2, that is equal to P1K upon 2 into V1 square upon C1 square. I have just replaced the formula for Mach number in terms of velocity of object to the velocity of sound wave. So P1 K1 V1 square rho 1 upon 2 K P1, that is equal to rho 1 V1 square upon 2. So replacing this term, I will have PS is equal to, wherever is P1 K m1 square upon 2, I am going to replace the new term like this. So I will have value as P1 plus rho 1 V1 square upon 2 plus 1 by 4 m1 square rho 1 V1 square upon 2 plus, in this term this m square upon 2 will get reduced and it will become m square m1 square upon 4 plus 2 minus k divided by 48 divided by 2 becomes 24. 24 into m1 raised to 4 plus so on. So I can have this PS minus P1. This rho 1 V1 square upon 2 will get common, will become denominator of the left hand side term, rho 1 V1 square upon 2, that is equal to 1 plus 1 by 4 m1 square plus 2 minus k upon 24 m1 raised to 4 plus so on. For compressible fluid, PS minus P1 upon rho 1 V1 square upon 2, that is equal to 1. Hence, if this is 1, then something is equal to 0. So we will have, for compressible fluids, it has a value greater than unity. That's all. Thank you.